Hola amigos! Today I'm back with a new tutorial that has been requested in the comments a few times, and that is the Dragon Ball teleport effect, also known in the show as instant transmission. This is a very popular effect, which has become a bit of a staple in anime shows as a way to mask characters or objects vanishing and reappearing. As we will see, this is a very simple effect to create, but the final result will depend a lot on correct timing of its parameters. In terms of difficulty, it is going to be a beginner to intermediate tutorial, combining basic Niagara systems with some medium-level material editing. And now, without further ado, let's start by looking at some reference footage of the effect that we are trying to achieve. Thankfully for us, there is a lot of reference images and video of this effect. Here's one on YouTube by EXP Chloe with every instance of it, at least until 3 years ago when the video was uploaded. Going through the footage at a slow speed gives us a pretty good idea of the timing and general balance of the effects, but let's pause it to take a closer look. We have only two elements here. The first one is the masking effect, which is removing chunks of Goku using these shapes. Speaking of the shapes, they are quite elongated vertically and look a bit like irregular, superimposed low-resolution triangles. Another thing to note is that the effect doesn't follow Goku's three-dimensional shape, and it's instead projected in 2D over the drawing. We could recreate this part of the effect using a post-process material, but since we might need to have multiple characters teleporting at the same time, we will make this on the character's own material. This way, we won't have to worry about the timing or having to use the stencil buffer to differentiate between targets. The second piece of the effect are these black thin lines scattered all over the character, which we can make using a particle system. The lines are vertical and go from very short to almost the same length as Goku's face. They don't move, and if we watch the end of the sequence, we can see they persist for a moment even after the character has vanished. And those are the two main components of this effect. Looks pretty simple overall. As I mentioned, having good references is essential to understand what we are trying to achieve. Now, before I continue, I know that there are multiple variations of the effect, probably as many as different animation teams or art directors have worked on each episode. I chose the original one from when the ability was introduced in the show because it has that interesting masking effect that others don't use. Additionally, to make a version like this one here, for example, it could be done simply by changing the color of the particles and tweaking the timing of the masking so it goes from 0 to 100% and makes the entire character flicker. In any case, I also thought that the original one was the coolest one to make. And now let's go back to Unreal and start working on our own version of this effect. Here is my basic setup. This is just a character that I imported from Mixamo together with a few different animations. One thing I didn't know when I downloaded it is that it uses two different materials, so we have to make sure that whatever effects we apply to one, we duplicate on the other. In an actual game production, you would probably want to create a master material for characters that can vanish using this effect, and then instance it with different parameters and textures for each one of them. For this tutorial though, I will simply copy and paste the nodes from one material to the other once I'm happy with the results. Now let's open one of the materials, I think this one is the torso, and see what we have here. Now, there's a lot of stuff that we don't really care about, we just want to make the character invisible. So we need to change either the opacity or the opacity mask. Now to enable this, let's select this node and change the blend mode from opaque to mask to enable this opacity mask. Now let's add a texture sample node to sample an image, we need to find an image that we're going to use to create this mask. I have this Voronoi noise texture that I made for a different video and which you can download from the link in the description, which I think will work great for us. But now, before we connect it to the opacity mask or we do something with these values, let's connect it to the emissive color so we can easily see how this texture is mapped onto our character. Let's go to the viewport and take a look. Oh, well, let me hide the post process for a moment so we can get rid of the depth of field. Perfect. Now, this texture can work once we stretch it. I think these shapes are triangular but kind of irregular enough that it's gonna achieve a very similar effect to what we want. But right now this texture is using the UV coordinates from the character's mesh and we want a 2D effect. So let's go back to the material and fix that. We could try simply using a screen position node, getting the viewport UV, and connecting that to the UV input of our texture sample. However, that won't really work if the character or the camera moves while the transition happens. Or at least I don't think it looks very good if it's too obvious that the effect is mapped to the screen. So let's go back to the material and get rid of this screen position, and let's make a bit of room here. Now on the node list, search for world space. And we have this world space align screen coordinates, which, as the description says, maps the center of viewport UVs to a world position. Now we could double click and go into this function and explain how it works, but then we should also explain this transform to clip space, and both things would take an entire tutorial all by itself. So for now let's use this function as it is, and as this input for the center point world position, let's search for object position. Now this gives us the position of this object or the character in world space. So now these screen aligned coordinates are going to be centered on our character. So let's get this offset and scale UVs and connect that to our texture sample. Now this looks a lot more promising. The effect is still mapped to the screen, but it's still centered on the character and it scales appropriately when we move the camera in and out. So this is great. Now we need just to tweak the scale of these UVs to adjust the texture to our desired scale, which in our case is going to be stretched vertically a lot. To scale the texture, once the UVs are aligned with the screen, so after this node, we need to multiply them by a vector 2D. So connect a multiply node to this offset and scale UVs output, and since we might want to tweak these values once we start using this texture as our opacity mask, let's also add a vector parameter. We can name this to something like maybe UV scale. And we need a vector 2D, we need to use also a component mask to filter this RGB and get only the red and green, or in our case, the U and V values. Now we can replace the input UVs in our texture sample, and we want to stretch this texture vertically and have something resembling triangles. So let's start by multiplying the X or green red component by a large number, maybe something like 10. And now each version of the texture is stretched, so it's a lot thinner and starts to be more like those vertical shapes that we were looking at earlier. Now we can also tweak the green component, or the Y or V, and multiply it by something like 0.5, and that will stretch the texture in this axis, in the vertical axis, but maybe I'll keep it at 1 for now and see how it looks. Hit save or apply and go back to the viewport. And now this is a lot more promising, and we can start to see some of these shapes that are very similar to what we were looking at earlier on the YouTube video of the show. So the next step is going to be using this texture in some way as our opacity mask. So let's go to the material and see how. To help me explain this next part, I temporarily changed the base color output of the material to show only the red channel of the texture. Now, to use these grayscale values as our opacity mask, first consider a hypothetical function that we could use to compare a grayscale value, going from 0 to 1, or black to white, with these shapes, one at a time. If the shape is brighter than the color we are comparing, or has a higher value, it returns 1, otherwise this function would return 0. So let's say that we start with a value of 0, or pure black. Now, if we compare pure black with each one of these irregular shapes, the function would return 1 for all of them, since even the darkest ones are a little bit bright, so they are brighter than black. But now, if we compare them with a mid-tone gray, let's say a value of 0.5, well, now some of these shapes are darker than 0.5, and some are brighter, so the function will return 0 for maybe these ones, and maybe these ones, and 1 for the rest. And finally, if we use any value higher than 1, so somehow brighter than pure white, none of the shapes will be brighter than it, because we know that the texture values only go up to 1, so the function will return 0 for all of them. Now, that function is called step, and it does exactly that. It compares two values, x and y, and returns 0 or 1 depending on which one is higher. Now we can go back to the material editor and use this step function to get our opacity mask. Give me a second to reconnect the base color and emissive color outputs. This is emissive and this is base color, and now we can add the step function. Remember, we're using the red channel of the texture as the X input, and for Y I'm going to add a scalar parameter. This is so we can control how much of the effect to apply later on. I'll change the name to transition, but you can use any names with any of these parameters as long as you remember them, since we might reference them later from a blueprint. Now we can connect this to the opacity mask, hit apply, and if we minimize this window, we can see if increasing this transition value makes our character disappear, and it's working perfectly. It doesn't look too different from the reference video from earlier. We have some shapes, slightly irregular, and because we're using the opacity mask and not the opacity, we get these slightly jagged edges that actually look pretty much like the reference. Great. And once we go past 1, the character becomes invisible. Finally, let's add a panner node between the multiply and the texture sample to displace the texture and add a few variations of the pattern. So search for panner, and it doesn't need a lot of speed, maybe something like 1.01 something and 1.01 something different. And now hit apply, and let's see how it looks. This will be especially useful if you play the effect in a slow motion, since we have now a few variations that disappear. Excellent. Now let's reset the transition parameter back to 0, and after applying and saving, we can move on to the Niagara part of this tutorial. Actually, before doing that, let's apply the masking to the other material. Let's open it, and for now, let's go back to the one that is already modified. Now, instead of copying and pasting all these nodes, I'm going to select all of them, right-click on any of the ones selected, and here at the bottom select Collapse to Function. Now Unreal asks for a name, and I'm going to name mine MF for material function, instant transmission vanish. Now Unreal replaces all the nodes with a call to this function, and we can open it by double clicking on it, but Unreal already opened the instance here. And the only change I want to make is this output. I'm going to rename it from step to something more useful like opacity mask. Or something like that. Now, apply and save. And let's go to the other material, and we can apply this function as well here. Now we can copy and paste. But in case you want to add calls to other functions, you can search for material function. And after adding this node, we can go here and search for our instant transmission function. Finally, we can also drag it from the content browser, and you can see there's 3 ways to add calls to custom functions. Now we cannot connect it to the opacity mask, or we can, but it doesn't work until we select the material and, like we did before, change the blend mode from opaque to masked. And now both materials are ready, and we can finally continue with the second part of the tutorial. Let's right-click on the content browser and create a new Niagara system. From the template list, I'm going to use the minimal template, since we're going to build our emitter from scratch. Name this something like Niagara system, black lines. We can start by renaming the effect, maybe something like black lines or something similar, and now we can go from the top and turn it into our desired effect. I have talked about skeletal mesh sample particles in other tutorials, so I won't go into tons of detail on this one to keep things a bit shorter. I'll start by changing the sim target from CPU sim to GPU, which is technically not needed but will give us better performance. After doing that, Unreal throws up a warning about the system bounds being dynamic, which we could ignore, but except for rare cases, it is good advice to change them to fixed. Next, let's change the emitter state life cycle from determined by the system to determined by this emitter, and set it to infinite. We want the particles to be emitted constantly while the vanish effect happens. Now we need some particles, so still on the emitter update stage, let's add a spawn rate. And set this to a high value, maybe 5000 will do for now. After we spawn the particles, the emitter needs to sample the mesh of our character before we place them in its triangles. Add a sample skeletal mesh after the spawn rate module and start with setting the source mode to attach parent. So the emitter uses whatever mesh the system is attached to, and we don't have to change the effect if we apply it to a different character. I'm also going to change the preview mesh to this Mixamo character that I've been using, so we can see it in the editor, and the default as well, so we don't have any errors if the system doesn't have a parent for any reason. The only other change in the module will be to select surface triangles as the mesh sampling type, since we want the particles to spawn at the character's surface, not in its actual skeleton. Now, it is possible that when you change the sampling mode to triangles, you get a CPU access error message. Something like this. This is simply because, in order to work, Niagara needs to be able to read the mesh data from the CPU. Clicking the Fix Now button will change the setting on the mesh and solve the issue. After this, we can move on to the Initialize Particle module to set their initial settings. Let's start by setting the lifetime to random, and values may be between 0.05 and 0.1. I know that the lines in the show live for a single frame, but it plays at very low frame rate, something between 10 and 20, and here at 60 frames per second, 0.05 is still only 3 frames, so I think it looks better when played in slow motion, and it also causes less flickering when the project uses temporal anti-alias. Let's also change the color mode to direct set, and if we set it to black, our particles will disappear. So let's keep it white or any other bright color for now. Now, instead of perfectly round circles, we want thin lines. So we need to change the sprite size mode from unset to random non-uniform. The uniform part, or non-uniform, means that we can change the X and Y axis independently. Let's set to something like between 0.1 and 0.2 on the X axis, and between 20 and 30 or 35 on Y. Now we have these very thin stretch lines. And now, just in case, we want these lines to make sure that they are vertical, so let's change the sprite rotation mode, direct angle, and keep it at 0. With the particles looking the way we want, except for the color that will be changed later, we can proceed to placing them on the character mesh. Add a skeletal mesh location module and make the same changes that we did on the sample module earlier. Set the source mode to attach parent, the preview and default meshes to the character that you're using, and finally the mesh sampling mode to surface triangles. And now if we move the camera around, we can see that the particles are spawning on top of what looks like our character. Now, for the same reason that I added the panel to the masking material earlier, I want to add a tiny bit of change over time to these particles, just in case that the effect is played in slow motion. On the particle update stage, I'm going to add a scale sprite size and change the mode to non-uniform curve. Now I want the horizontal axis to stay the same, so let's isolate X and keep it at 1 throughout the entire life of the particle. And I also want the particles to scale down vertically, so let's make them go from something like maybe 2 to 0. Now we barely can see this in real time, so you might not need it in your project. Once that's done, we can see how to change the color to black. Select the sprite renderer, and here the solution is as simple as going to the default sprite material that these particles are using and changing the blending mode from additive to translucent. The reason it wasn't working when we set the color to black is that adding a value of 0 in additive mode doesn't change the color. So we can hit apply, save, and if we go to our particle system and on the initialized particle change the color to black, now we have the particles that we're looking for. Now the particles are looking great, but we need to be able to turn the effect on and off when the vanish transition happens. To do that, we can add a new user parameter of the type float. I'll name mine density, and then go to the spawn rate and change it from a constant to be a multiply float. One of the factors can be set back to the 5,000 units that we had earlier, and we can drag our density user parameter on top of the second one. So now, when density is 1, we get 5,000 particles per second, and at 0, the effect will be stopped. And that covers the Niagara part of the tutorial. Now, let's save and head over to the character blueprint and put all of this together. Since this tutorial is focused on the material and Niagara aspects, I went ahead and made my edits on this character, but I will review how everything works. The first thing that you'll need to do is create a new Niagara particle system component, attach it to the skeletal mesh of the character as a child, and in the particle system, select the asset that we just made. In my case, Niagara system black lines. Also, I didn't do it for this tutorial, but you could instead create the system only when the character teleports or jumps and destroy it afterwards. But anyway, with no particles spawned, the cost in performance when the effect is off is minimal. Going to the event graph, the other thing that you'll need to do is create dynamic instances of the materials that you want to make disappear and create variables to reference them later. This character uses two materials, so I need two copies of the create dynamic material instance node, one for element index 0 and one for element index 1. A quick way to create the reference variables is by dragging the return value of the previous node and selecting Promote to Variable in the context menu, saving a few steps. Something to note about these nodes is that in this tutorial I'm creating these dynamic material instances and these variables in the Begin Play event, but depending on your project needs, you might want to do that as part of the construction script instead. Next, my simple character is set up to play a couple of different animations on key presses or key releases, 1, 2, and so on, triggering the effect, but you will need to adjust the next part according to the way characters or abilities work in your project. For example, if you have a function that is triggered when the character teleports, you might want to put these nodes on that function instead. And now I'm going to show you a couple ways of controlling the dynamic material parameters, but only one to control the Niagara user parameters, and I will explain why once we get there. The first method, which also works with Niagara systems, is using blueprint timelines. To create one, right-click to add a node and search for timeline. After adding a timeline and giving it a name, we can double-click on it to edit it. Now we can add tracks, which are just variables that will change over time as the timeline plays. And we have tracks for floats, vectors, events, and colors. In our case, we need two tracks, one for the material parameter, which controls how much of the character disappears, and a second one for the particle system, which controls the density of the effect. The other thing that we need to change is the length of this timeline. We don't want to keep playing after the animation has been done. Now you will need to change that number based on the length of the animation that you want to play while the effect is running. In my case, I have this animation here, and I want the effect to start right at the beginning and be done by the time the character points forward. So instead of using the entire length, I'm going to have a timeline with a duration of maybe 1 or 1.1. So I would change this length to maybe 1.1. Now you can right-click on the curve to add keys and just move them and change the interpolation the same way that you do with any other curve in Unreal. And I will show you the way I edited mine. So going back to the event graph, let me get rid of this one and double click on mine, and this is the curve for the vanish effect on the material, and this is the curve for the particle density, and the effect goes up to 0.3 a couple times, like blinks the parts of the character just very quickly before at 1 second it's fully invisible. The Niagara system, as we can see, it's a little bit delayed but follows a similar pattern, except that it stays after 1 second all the way to 1.06, maybe 1.08. And this is for the vanish effect, when the character disappears. Now, on the other animation that I have here, the second timeline, the effect for the particles is very similar, but the effect for the track for the material parameter is inverted. So at a value of 1, the character is invisible. So we have these values actually a little bit higher than 1 to make sure that there's no little pieces of the material visible. And it blinks a couple times just before it becomes fully visible. Save, go back to the event graph, and once you add tracks to your timeline, in this case one is called vanish, the other is called Niagara vanish, you have outputs in your node that correspond to each one of them. Now, to assign that, to use that as our material parameters, first we need to use this node called setScalarParameterValue, and then change the parameter name to match the parameter name in our function. In our case, I call this one transition, so the parameter name needs to be the same. And as our target, we're using the references to the dynamic materials that we created earlier. The second output of this timeline corresponds to the particle system. So it's being used in this node called setNiagaraVariable for floats, and the particle name or the particle user parameter name is called density. The target is the Niagara system component that we created here, and the value is the output of the timeline. So now if we save and I go back, when I press the 1 key on my keyboard, the character disappears, and when I press 2, they reappear again. Great. Now let's see the other way that we can control these material parameters. The second method, which I'm using here for the number 3 key, involves using animation curves. As we can see, there's no timeline, and if I go to the animation that plays when I trigger this action, which is here, we can see that I added a curve called transition, so it matches the name of the material parameter on the dynamic instances. So transition was the same name here that we used on this setScalarParameterValue when I was using the timeline. And if the names of the curve and the material parameter are the same, and if the curve is set up to be used as a material, which we can check here, then the value from the curve will affect the material. And if we double click on this curve to go to the editor, this makes editing the curve very easy, because you can see the effect of the values live on the animation as it plays, which is super helpful. And sadly, the only option to do this with Niagara user parameters involves a workaround using parameter collections that have to be updated every other frame from a tick event, which I didn't like too much. Another possibility would be to bake the timing of the particle effect and have a user parameter that we can set for each character, and that way the effect wouldn't loop and could be triggered using animation notifies. But I already had made the effect in this way, so unless you find a better system, I would recommend to stick with the blueprint timeline option. And that is all I have for this tutorial. I know that it was a shorter and easier one than some of the last ones, but not for that less fun. I hope that you enjoyed it, and if you did, consider giving a like and subscribing to see more content like this. And if you have any ideas or suggestions, or any particular effect that you've seen and want to know if it's possible to recreate in Unreal, leave a comment below. See you next time!